Hello students, now we are going to discuss the physical properties of boron family, that is group 13, the physical properties. You know that group 13 to 17 all are and almost all are non-metals. They are behaved just opposite of the metals, group 1, group 2 and the transition metals. So what are the basic properties, what are the important properties of group 13 elements, that is boron family? Let us discuss. First is physical state. The physical state, all boron family, all are solids. All are solids. Boron, aluminum, gallium. What are the names generally? Boron, aluminum, gallium, indium, thallium. All are solid. And gallium, if you see the intermolecular attraction, gallium, the structure of gallium is very weak. That's why gallium is shows semi-solid. Because at room temperature also gallium melts, but generally at room temperature all are in solid state. Okay. Then metallic, non-metallic nature. Metallic, non-metallic character. If you see metallic, non-metallic natures, then generally boron is non-metals. Boron is non-metal. Aluminium to gallium, aluminium to thallium, all are metals. Aluminium to thallium, all are metals. And here boron is non-metals. Electronic configuration. Electronic configuration. The general electronic configuration is Ns2Np1. It has 3 electrons in its outermost shell. 3 electrons in its outermost shell, that is Ns2Np1. And if you see the configuration, boron, that is 5, can be written as helium 2, 2s2 2p1. Aluminium 13 can be written as neon 10, 3s2 3p1. Gallium 31 can be written as argon 18, 3d10, 4s2 4p1. Indium, that is 49, can be written as krypton 36, 4d10, 5s2 5p1. Then thallium, that is 81, that is xenon 54, then 4f14, then 5d10, 6s2, 6p1. So this is very important, thallium configuration and gallium configuration, if you see. Because you see the difference. In case of gallium, d orbital starts. Filling of d orbital starts, that is gallium. But in case of aluminum, d is vacant and boron also d is vacant. And the indium, here indium, d also occurs. So this is the main difference between electronic configuration of elements of boron family. And as they have 3 electron outermost shell, generally they shows valency 3. Common valency, if you see valency shows 3 and 1 also. Monovalent, when it use first, that is 3p electron, Np electron, it shows monovalent. When you use all three electrons, that is trivalent. Generally it shows monovalent and trivalent valency. Okay. Then number 4, atomic size. Atomic size, if you see that boron less than gallium, less than aluminum, less than indium, less than thallium. Only difference is here. Why? The size of gallium is smaller than aluminum, because you see gallium, what happens? D subcell contain 10 electrons. So as D subcell has pore shielding effect, D subcell has pore shielding effect. As it has a pore shielding effect in case of gallium, then the effective nuclear charge, Z effective, increases. Z effective increases. As Z effective increases, size decreases. So in case of gallium, you see in case of aluminum, no involvement of D subcells. Here involvement of D subcell. That's why D subcell cannot screen properly. So effective nuclear charge increases, so size decreases. That's why the size is gallium is smaller than aluminum. It's very important difference, atomic size. Then ionization energy. Ionization energy, if you compare, group 13 has smaller ionization energy, lower ionization energy than group 2. Why? Why ionization energy of group 13 is lower than group 2? Because it has configuration NS2 NP1. Electron will be lost from P. The first ionization energy of group 13 is smaller than group 2. And here it is NS2. Electron will be lost from S, which is already fully filled. That's why it requires more energy and it requires less energy. That's why it does not depend upon size, it mainly depends upon electron configuration. As electron lost from S, electron lost from P, but same cell. That's why it is lower ionization energy compared to 2, because it is stable. This is the ionization energy. But generally, I1 plus I2 plus I3 is very high. As the ionization energy is very high, generally they do not form plus 3 state. Free plus 3 plus generally not possible due to what happens? High ionization energy 1, 2, 3. To remove first electron, second electron, third electron require very high ionization energy. That's why generally they do not exist in 3 plus free state, because very high ionization energy. This is regarding the ionization energy of group 13 elements, and if you compare the ionization energy, boron is highest, then aluminum, then gallium, then indium, less than thallium. This is the order. Boron greater than aluminum, aluminum less than gallium, gallium is greater than indium, indium less than thallium. This is the order. Deviation. Why the deviation? Already know. Why aluminum less? Why gallium is more? Because due to small size. This is the answer. Here, indium, thallium, what happens? Because as thallium has F subcell, which has poorest shielding effect, that's why ionization energy of thallium is more than but the difference is very less, but higher ionization energy compared to indium. So this is the order of ionization energy comparison. Boron, if you write the order, regular order, if you write boron greater than gallium, greater than aluminum, greater than thallium, then greater than indium. This is the order. This is about regarding ionization energy. Then next is melting point. These elements also shows high melting point. Melting point order is generally boron greater than boron, then Aluminium. Here aluminium greater than gallium, gallium less than indium. Okay, then thallium. Here what happens that gallium is lowest. If you see, if you write the order boron, then aluminium. Actually order is boron greater than aluminium, greater than your thallium, greater than indium. Okay, greater than gallium. This is the order. B aluminium, then thallium, then indium, then gallium. Actually, this is the order. Melting point. The melting point depends upon the structures. The structure, if it has a very close packed structure, then the melting point will be maximum. With definition in melting point, why that gallium has a list that is very low melting point due to weak structures. That the structure cannot fit in the solid state properly. That's why the intermolecular attraction is weak. That's why it exists in very low melting point. And due to weak intermolecular attraction, weak, that is not a perfect structure. That's why the close packing is weak. This melting point, then boiling point. Boiling point generally that decreasing order. Boron greater than aluminium, greater than gallium, greater than indium, greater than thallium. In this order. Boron greater than aluminium, greater than gallium, greater than indium, greater than thallium. Here what happens that due to small size, boron, very strong intermolecular attraction of the boron, because all having crystalline structures. Are the crystalline structure solid state, it depends upon the attraction, intermolecular attraction. Boron is maximum here. So boron greater than aluminium, greater than gallium, then indium, thallium, boiling point order. Then density. Density also that decreasing order. Boron less than aluminium, less than gallium, less than indium, less than thallium. This is the increasing order of density. Density increases from boron to because increasing volume, increasing mass is more than. Here what happens? Increasing mass is more than increasing volume. This is the difference. Increasing mass is more than increasing volume. That's why density increases. So boiling point, density, melting point, ionization energy, then electropositive nature. The electropositive nature, if you see, here what happens? Generally first increases. Boron is less than aluminium. Boron to aluminium increases. Then what happens? Then decreases. Gallium, then indium, then thallium. Here if you see the order, here maximum is electropositive character is aluminium, because aluminium has more negative reduction potential. The reduction potential is more negative for aluminium, that is minus 1.66 volt. As it has more negative reduction potential, so very better, it is viewed as more metallic character, more electropositive character. So metallic character aluminium is maximum because it has more negative, more is the very low is the reduction potential, more is the reactivity, and more is the metallic character. So electropositive character of aluminium is maximum. Least is no doubt boron, least is boron, but maximum is aluminium, electropositive character, the electronegative nature. electronegative nature, electronegativity you can say, electronegativity order is that maximum is boron, then thallium, then indium, then boron, indium, thallium, indium, then boron, greater than thallium, greater than indium, greater than gallium, greater than thallium, aluminum. Why? Thallium is coming due to pore shielding effect of F subshell. As F subshell of thallium has pore shielding effect, that's why the electronegativity character is more of thallium. Exceptional character. Although it's a larger size, but electronegativity is more next to boron due to pore shielding effect of F subshell. So some variation observed. Then that last one is very oxidation states. It generally shows +3 and +1 state. Boron family generally shows +3 and +1 state because it has 3 electrons, that's why +3. As it has one subcell having 1 electron, 3p, one subcell is there, 3p subcell having 1 electron, that's why shows +1. But +3 stability decreases down the group. +3 stability decreases down the group, but +1 stability increases down the group due to inertia effect. Due to inertia effect, you know this. In case of thallium, you see, as pore of 14 electron is there, due to pore shielding effect, this 6s2 electron is more penetrated toward the nucleus, more attracted toward the nucleus. So it has a little tendency to participate. So only 6p electron takes part. That's why thallium plus is more stable than thallium plus 3. Thallium plus is more stable than thallium plus 3. And that's why your thallium chloride is ionic, but thallium trichloride is covalent. Thallium trichloride is covalent, but thallium monochloride is ionic. Due to this inertial effect, thallium plus is more stable. And also is very important question, due to this stable oxidation state, gallium, that you write down is very important, that indium and gallium, you can say, gallium also, gallium plus 1 undergo disproportionation reaction forming gallium plus 3 and gallium. Similarly, indium also, indium plus 1 undergo disproportionation reaction forming indium plus 3 and indium. You know what happens? Here the same oxidation state, unstable oxidation state, gets oxidized and reduced. It is oxidized to gallium plus 3 and reduced to gallium. This reaction is called disproportionation reaction. Disproportionation reaction means a particular ion, that is unstable ion, gets oxidized and reduced. It will be oxidized and it will be reduced. Same ion. That is called disproportionation reaction. That's why gallium plus, indium plus shows disproportionation reactions. So these are some important physical behavior of boron family. That almost all cases, properties, some exceptional behavior is there. Try to remember the exceptional properties and you note down and you read this one. What are the deviation in the series? Okay, it will be helpful for your competitive examination. Okay, thank you all.